Ladies and gentlemen, today I want to go through the assignment, and before we do the Making Sense of Emission Spectra assignment, I want to make sure we're clear on the what an emission spectra is and what the lines represent, so that as you're going through the activity, you should be getting a deeper understanding of what each line that appears on the different elements spectra represents. Okay. To help with clarification, I did load a summary of the lesson we did yesterday, so a really concise version of what we covered yesterday is in this document right here, so you can either preview that or print it out, open it up. The document we're going to be working on today, the assignment we're going to be working on today, is this Making Sense of Emission Spectra. All right. So one of the things that we want to take a look at is the actual emission spectra for a couple elements. The first thing we need to understand is how these emission spectra are actually captured. There's a couple of different ways. One is using a prism. The other one is using something called a spectrophotometer, which is basically a bunch of little prisms spread out over a sheet of clear plastic. Once you shine a narrowed beam, so kind of a slice of the light going through into a prism or onto a spectrophotometer, what happens is that the density of the material you're shining the light through causes the light to be broken down into all the different wavelengths that exist. So you spread the light out, you diffract it, and you are able to see all of the different wavelengths, colors, frequencies of light that exist in the light you're shining into the prism. If it's white light from the sun, then you end up with the whole Roy G. Biv, red, orange, yellow, green, blue, violet spectrum. Okay? However, if we take light from specific elements, what we don't have is a continuous spectrum. So this would be like sunlight. Sodium, if you heat that up to a point where it starts to glow, gives off very distinct lines of light. Okay? And all these lines of light are going to help us determine how many different jumps there are between energy levels in the cloud, and where the majority of those jumps are and the kind of light that's going to be given off. So sodium gives off a yellowish orange color whenever it's excited. That would make sense if you look at its spectrogram, because you have a lot of very bold lines in that yellow range. Okay? Hydrogen looks much more like a black light. Black lights have that kind of violet, ultraviolet color to them, and look at where the majority of their lines are, down here in the violet to blue range. Okay? And the other thing I want you to notice, as we go from hydrogen, 1 electron, you have 4 different jumps. Sodium has 11 electrons. You have more jumps. Calcium has 20 electrons. Look how many more jumps there are, how many more lines. And look at these lines that are thicker. Those represent 2 or 3 different jumps in that energy array. So what do these lines really represent? If we take a look at this very crude model of lithium. Lithium has 3 protons and 4 neutrons in its nucleus. It has 3 electrons, 2 on the first energy level, and we're going to learn later on that that's the capacity for the first energy level, and coincidentally, really not coincidentally, but there are 2 elements on the first row of the table. There are 2 electrons that can fill in the first energy level. Lithium happens to be the first element on the second second row of the table, which means it's going to have one electron on the second energy level. Okay. Now, when these electrons are excited, so these would be the ground state. This is where they exist whenever they are just in their normal state. We start to bombard lithium with electricity, or we start to heat lithium up to the point where it starts to glow. What we're going to see is that you're going to have electrons are going to jump out to higher energy levels. That would be its excited state. So this is the ground state, and that's your excited state. Okay. This one might jump out to the fourth energy level. That's your excited state. That's your ground state. This one might jump out to the fourth energy level. This is your ground state. This would be your excited state. Okay? Now, they can't stay there forever. So the energy is absorbed, whether it's electrical energy or heat energy, and then they drop back down. When these guys drop back down, the farther the drop, the more energy that's given off. So if we compare these three, this is the lowest energy, the shortest movement between energy levels. So when this drops back down, when it drops from the excited state to the ground state, it's going to give off light, and that light's going to be red. This one here, this is kind of in the middle. It's not the biggest drop, but it's not the smallest drop either. This one, when it goes from the excited state back to the ground state, is probably going to give off something in the range of a green light. Okay, green's kind of in the middle of the Roy G. Biv spectrum. And then this one down here, it's kind of probably the biggest one we have, but it's not enormous. So we'll say this one's probably going to give off blue light whenever it goes off. So each line on the emission spectrum, represents a fall from the excited state back to the ground state. Light is given off when electrons return to their ground state. Okay? Now, with that in mind, there is one more thing I do want to take a look at with you, and that is the last page of that summary has a kind of an infographic, if you will, a big summary chart, and this has all the key definitions, the equations, explanations of energy and the electromagnetic spectrum. But the thing I really want to focus on before we bug out of here and start doing the lesson for today is I want you to notice right here, I put this section of wave basics. Wave basics includes the definition of wavelength and frequency that I asked you to do yesterday as part of your assignment. Wavelength, again, is the distance between identical points on two neighboring waves. So crest to crest or trough to trough on neighboring waves. That distance is your wavelength. How many of these waves, 1, 2, 3 waves, go by per second, that's frequency. And it's usually given in a unit called hertz. All hertz means is per second. So if this is the number of waves that went by in a second, we would count them as 1 wave, 2 waves, 3 waves. The frequency would be 3 per second, or 3 hertz. Okay? Now, if we go back to our simulation here, our lesson, you want to open this link. This link will open this simulation. Okay? This simulation, you need to do a couple things before you start. First thing is you want to click on multiple atoms. Okay? Second thing you want to do is down here at the bottom, you want to make sure the spectrophotometer is clicked. So you want to see this at the bottom, and you can do the squiggles or not. Either way, if you want to really see
the jumps and falls if you do run in slow motion, and the squiggles, you'll see where those are coming through, and you can just hit reset and it will start over. Okay? The run in slow motion and the squiggles are not necessary, but what you are seeing here are electrons at the ground state jumping up to the excited state and then falling back down. You can select the different elements from that drop-down menu, and what you're going to notice is the light that are coming off here. You can see these light particles, these photons being given off. Each one of those photons has a band in the spectrogram down here at the bottom, and you're going to want to recreate these on your lab, so pay attention to the markings of where the lines are on the scale. And whenever you go to the actual activity here and you come down to the bottom, for each element you're going to want to use your palette here to pick the right colors. You can pick all the different colors that you need. So if we're going to do a red line somewhere between, it was about 650, draw a red line in, figure out where your other lines are, pick the correct color, and recreate those. Recreate those lines, those graphics, and then you're going to use those to answer the questions here at the bottom. You should be able to use your text box tool and just type your answers right in to the activity itself. Make sure that this is submitted before I see you tomorrow morning. We'll go over this together. If you want full credit, it needs to be done before the start of class tomorrow. Okay? And then we'll go over it together, and you can make any corrections that you need to make. All right, well, have fun exploring the emission spectra. If you have any questions, feel free to shoot me an email, and we will see you on Wednesday.